We wrapped up chapter 3 last time. We will go back to chapter 4, but I think, after spending so much time on the transformer as a component, it sort of gets boring. So the idea is, if we go to chapter 6, we get a view of the system quicker. We look at the big power system and how are we going to solve these big power system problems. And then we go back to another component, which is the transmission line. But really, all we're going to get out of the chapters, I sort of group chapters 4 and 5 together together as chapter 4, as transmission lines. And really, the major outcome from that is that the transmission line model looks something like this. Right? And this is one transmission tower, another transmission tower. Right? So this is the transmission line between some towers. We have to model it, like we did for the transformer, and we said, okay, the equivalent circuit with a transformer is either this phase shift with a series impedance somewhere, primary or secondary, in per unit, or just a pure short circuit with a series impedance. Right? That's really the outcome of chapter 3. Right? So we spent a lot of time, I understand, but really the outcome was the major outcome from a power systems perspective. Right? Chapter 4 and 5, or the transmission line, is another component level chapter. We can spend a lot of time studying transmission lines and flow of waves on transmission lines and reflected wave theory. I don't know if you studied the idea of reflected waves and stuff in electromagnetics. Have you studied that? Yeah, so we can spend a lot of time doing that on transmission lines as well, right? But we don't, right? So at the end, because at the end, I want to study the component a little bit to help me assess how I can use it in a big power flow or a load flow system model, right? And we will see what the objective of a load flow or system model is. So because that's really mainly the objective behind what we're doing in this course. There are people, if you're going to be designing transmission lines, of course you have to understand all these other phenomena, right? When a lightning strike comes and hits the transmission line, how does this transmission line behave? Right? We don't get into that too much in this course, right? This is more of what we're studying is more of the steady state performance of the power system, right? So what we are going to need is to build our single phase equivalent circuit, right? Everything we're doing is building a single phase equivalent circuit. So what we're going to need is to understand that the transmission line can be modeled in a single phase equivalent circuit of the transmission line can be modeled as a series resistance, which is the transmission line's resistance, a series inductance, and a shunt capacitance. This shunt capacitance resembles what? Resembles, you have a transmission line with a voltage across, voltage on the cable, on the conductor, right? So this conductor is connected to the high voltage side of a transformer somewhere, right? There's a generator somewhere, transformer somewhere, and then fine, you go to the transmission line. Of course, 3-phase, right? But this is sort of the single line equivalent circuit of it, right? So this is a live line, right? This is a high voltage line. So it's like a capacitor, right? So there's a high voltage charge on one end, charge on one plate, and then the other capacitor's plate is, connected to ground, for example, has a different charge. So the same thing happens between the transmission line and the structure, which should be grounded, because you can go up and touch the transmission line tower, and of course Earth, right? We will talk about what Earth means when we talk more about protection. But basically, the structure is grounded at some point to make sure you can go up to it and touch it, right? So there is a potential difference between the charge on this transmission line and the surrounding tower and ground, right? So this we sort of resemble as this capacitance, right? And what we do is, and then this is, we remember everything we're doing is in terms of admittances, or everything we'll do in this chapter will be in terms of admittances. Admittances are nothing but the reciprocal of the impedance. And admittance is like impedance. Impedance is equal to R plus Jx. Admittance is equal to G plus JB, right? This is conductance and this is susceptance, right? So this is nothing but reciprocal of impedance. So we will typically calculate, or what we'll do in chapter 4 actually is calculate the capacitance between this transmission line and ground. And this transmission line and ground has a certain capacitance that will act at this side of the transmission line and at this side of the transmission line. Right? So we sort of divide that capacitance into two. And we call this JB over 2, JB over 2. Right? So this is really what you're going to be calculating. This is the outcome of chapter 4/5, 4 mainly. Right? Is this single phase equivalent circuit model of the transmission line. And we call this the short line model. Right? There are many models for transmission lines. Right? Depending on what you're going to do with it, if you're going to be using it for a steady state power flow, if you're going to be looking at transient, if you're going to be looking at effects of lightning, depending on what you're going to do with it, there are different more useful models than others, right? So we will typically use this short line model, which is a good approximation for how a transmission line behaves up to 100 kilometers of length, right? So it's a pretty good model for what we need to do in a power flow type situation. So this is what we will be doing. There's a medium line model and a long line model. So we will not even study those. Right? But you need to know, okay, but we will derive this. This we will derive in chapter 4, right? But for now, okay, this is what it's going to look like. This is the outcome of what we're going to do. And this is what we're going to stick into our single phase equivalent circuit, right? At the end of the day, I can put now what? If I have a transformer before this, I can put an impedance for the transformer. I can put my voltage source for the generator and close my loop, right? This is really what I care about, right? The single phase equivalent circuit of the system. So that's why we will spend more time on a component level again later. But for now, let's see how we take all these components, the transformers, the generators, transmission lines, and put them in a big system. And how do we solve the system and use it to look at how a city grows, for example, or how do you size components for a city, or what if you have failures in different places of the power system? How does the power system behave, etc., etc., right? So that's the objective of this chapter. Okay. So this chapter is called Power Flows, and it's nothing but really it's the steady state solution of your single phase equivalent circuit. That's what it is, right? The only difference now is typically in a 214 type circuit, you have a limited number of nodes, and you typically are able to calculate the voltages at the various nodes using nodal voltage analysis, etc., right? In a power system, you are typically not given voltages and currents. You are typically given powers, right? You're typically given a generator with a certain power that has to feed loads with a certain power, right? And given this information, how do you solve for all the system voltages? And at the end of the day, all we need to do is figure out what current is flowing in every branch and what voltage is at every node. Really, that's what we're trying to do, the same as 214, right? The only thing is we are missing lots of information because of the way that the power system problem is formulated. And I will show you how what I mean in more detail. But the idea is you are given you have to utilize the powers that you're given, powers that you're given at the various nodes to be able to solve for voltages and currents. So in a typical circuits problem, you would typically use V equals IR or IZ to solve for voltages and currents everywhere. So the voltage difference, V in between two nodes, will help you calculate the current knowing the impedance, right? But what if you don't know the impedances? You don't know the impedances of your motors, you don't know the impedances of your transformers, for example. You would be given a load that you want to feed, right? And you want to see how your system will behave in that case. So this information, this power information is something that you need to utilize, right? And we have another equation in power systems, which is this, the power equation. Really, these are the main. So we have the power equation, and we have Ohm's law, right? We don't have anything else, right? We're going to sort of combine both to maybe solve for I in terms of V and Z, or in our case, we will actually solve for I in terms of V and admittance, right? So and then substitute that here, and then utilize now the power information that we have, that we're going to be given. We're going to be given lots of information about powers at different nodes, right? So we're going to be able to utilize the power information, and using the voltage and the voltage vector and the admittance matrix, we will be able to take that and plug it in here and come up with an equation. This equation will have some unknowns. The major unknowns that we're trying to calculate are basically, what we want to do is find out how current is flowing, right? So between two nodes in an AC power system, for us to be able to find out how much current is flowing between these two nodes, I need to know the voltage and angle here, and the voltage and angle here. If I do that, that's it. If I know the voltage and magnitude and angle at any bus, I can know the current flowing between the two buses, right? Between the two nodes in a power system, right? In a DC circuit, you only need to know voltage. In an AC circuit, you need to know voltage and angle, basically, to be able to calculate the current flow. So we will be constructing a system of equations, right, in terms of power, both real and reactive power, right, and all the voltages and admittances that we have in the system, right? And sometimes we will be given power. And so we have now what? 4 variables, really. So we have power, real, and reactive. And we have voltage. Admittances we will know. The admittances of the transmission line, the admittance of the transformer, we will know the admittances that we have in the system. But what we won't know is the voltage magnitude sometimes, or the angle. So we have power, real power, reactive power, voltage, and angle are our 4 variables in the system that we will construct. Right? These are the 4 variables that we have. So sometimes we'll be given 2. I mean, we will always have to be given 2 to find and find the other 2, given a certain number of equations, right? If you have 2 unknowns, you have 2 equations to find the 2 unknowns, right? So in a power system that is composed of 10,000 buses, right? So you will have a ton of equations, right? So we'll see how to solve these, right? And we will see how to simplify something like that, right? So again, it's nothing but solving the circuits problem, right? But now you have a 10,000 node power system. So how do you solve that? You're not going to be putting things in parallel series and then expanding again to find the current using current divider rule and stuff like that, right? So we will utilize numerical techniques. And in this chapter, the book talks about 2 methods for numerical analysis. We will just utilize one, right? So and this one is actually utilized in Power World. So you can actually simulate all the problems that we do in this chapter using Power World, and all the numerical numbers that so after iteration 1, you want to see if your numbers were correct or not. The numbers are actually, the iterations are actually created in Power World, and you can actually look at each iteration, the solution until the system converges. So you've all taken some sort of numerical analysis course before? No? No numerical methods course at all. It's fine. So anyway, we'll introduce you to one of the numerical methods techniques. Even in College Station, you have not taken a numerical analysis course. So we will introduce one method of numerical analysis that will help us solve a system of equations. We'll go through it in this class. We won't dwell on the theory of the numerical analysis. Of course, I will just show you, okay, this is the numerical analysis method. So its proof, I will not talk about. This is not a math class. I will not talk about the proof of the numerical analysis method from the origins of Taylor series, etc., etc. Right? But I will talk about the numerical analysis method itself and the various steps to carry out the numerical analysis method. Yeah. So, and the idea is to solve your circuit. But this circuit has many, many nodes, and that's the problem we have. Okay. So we will, as I said, talk about iterative or algebraic techniques required to solve a big circuit. We will talk only about the Newton-Raphson method. I will not go through the Gauss-Seidel method, just because I prefer to cover other material in the textbook. We will definitely push a lot on using Power World in this chapter. There's a lot of use of Power World here. And Power World uses this iterative method to solve the power flow problem that you pose to the Power World simulator. And then we will talk about, okay, now we've solved the circuit. How do you control power flows? So you have a very congested power line. That transmission line is overloaded, or this area is congested, meaning the lines in this zone are overloaded. How do you move power, route power differently, right? Our electrical power system is basically a set of voltage sources, which are generators, and then impedances. You connected them together with transmission lines or cables, which are also impedances. You turn everything on, and current will flow based on the impedance, right? You have no control, theoretically speaking. But how do you manage to control it? I mean, you cannot live with that. So we add mechanisms in the power system to control power flow. And these mechanisms, I mean, we've studied one, transformer. The tap changing on a transformer is one method to control power flow, right? What you want to do is, again, the voltage, the magnitude, and angle is what controls power between two nodes. So if you change the voltage magnitude, you've controlled power in a certain fashion, right? And we also studied phase-shifting transformers. I mean, the idea of a phase-shifting transformer, one simple phase-shifting transformer is a star-delta transformer, right? It gives you a fixed phase shift. There are other problems in the textbook, in the homeworks that I haven't assigned, but you can look at them, right? In these problems, you can create other phase shifts, right? So it's not a fixed phase shift. And you can, of course, create something with a variable phase shift. We did not study it. It's in the textbook, but I didn't study that. I mean, the concept, I just want you to look at. The concept is you can phase shift. If you can phase shift, meaning you can change the angle, that means you can control power between two nodes or current flowing between two buses, right? So this is one method. One method is changing voltage magnitude. One method is changing voltages and angle. The other method of changing voltages and magnitude would be what? So you have these impedances in your power system. Most of them are reactances, inductors, right? These inductors will have voltage drops associated with them, right? Anytime you have currents going through a reactive element, there will be a voltage drop. How do we negate the effect of an inductor? A capacitor. So, because then your system will look, again, if you assume there is no resistance, assuming there's no resistance or very little resistance, then the voltage drops in the power system are mainly due to inductors. So you have a big inductive power system. So how do you negate the effect of these inductors, which are causing voltage drops? So they are consuming reactive power because we need it, right? But how do you sort of negate their voltage drop effect? By supplying them with the reactive power locally. That's the scientific thing that we're doing, right? But from a circuits perspective, somebody from 214 that did not study power systems or does not understand what reactive power means or why a generator needs reactive power, a motor needs reactive power, a transformer needs reactive power. From a circuits perspective, we know that if I want to negate the effect of an inductor in an AC circuit, simple 214 basis AC circuit, I will put a capacitor. And then the source is seeing what? The sum of the impedance. Impedance is a resistor and some inductor and capacitor. The inductor and capacitor, I chose them so that I have negated the effect of the inductor completely. You can do that, of course. And then in that case, it's a pure resistance. Right? Do we want to do that? Typically not. I will show you why. But towards the end of this chapter, we understand why generators like to operate with some lagging power factor. But for now, you can negate that by putting these capacitors. You put these capacitors, from a circuit's perspective, what does it do is eliminate the voltage drops really caused by the inductor, as if they're not there. They're both together, they disappear. From a circuit's perspective. Really, they're not disappearing, of course. They're still in the system. But what's happening is that all the reactive power required by the inductor is being produced by the capacitor. Remember the initial in chapter 2, we were talking about power in an inductor and power in a capacitor? Power in a capacitor and power in an inductor was at double the frequency, but they were 180 degrees out of phase. One was leading the voltage by 90, one was lagging the voltage by 90 in current. So the same voltage is applied to an inductor and a capacitor. One will have current leading by 90, one will have current lagging by 90. So there's a 180 degree phase shift between the currents, right? So you multiply the voltage and the current by each other, you get power. So power in capacitors and power in inductors is complementary. It's 180 degrees apart. So one is producing reactive power, one is generating reactive power. One is producing reactive power, so that's why they sort of negate each other from a circuit's perspective. But physically, they're both there acting and doing their job. Right? So adding capacitors in the power system is another way to control power flow in the power system. Right? And you can do that, as we said, as a fixed capacitor, or you can do that as a switched capacitor. You switch these capacitors into the system, or you can do that via power electronics, which is what is called a static voltage compensator. SVR, or a static VAR compensator. That's and they do that not only at the transmission level now, they sort of try to do it now at the distribution level as well, right? So it's at both levels. So that's how we would, we would need to figure out how to control the power system, power flow in a power system that way. Okay. So with the power flow problem, or the power flow solution that we're going to reach for a power system, we will ensure that the generation supplies the demand plus the losses. We will make sure that they are matched. We will match that, and we will see. We will look at every bus, and we'll see how much power are we generating, how much load is on the bus. Okay, we want to make sure that generation meets demand not at that specific bus, for the full power system, which means that there will be a relationship between the powers that all the buses and that in a power system. So the full power system will have a solution, right? Like a circuit, it will have a solution. There is one solution for your electrical circuit. So we will have to come up with that. But how do you come up with that in a big power system? So we will ensure that this happens. So bus voltage magnitudes remain close to rated values. So we want to make sure that when we run the power flow simulation and we reach steady state, that all the voltage magnitudes are close to 1 per unit. And we look at and then you will, again, in the power flow problem, in the power world, you will go in and you put the parameters for the transmission lines that are connecting all these buses together, right? And one of the parameters is the rating of the transmission line. You will buy a transmission line rated for a certain amount of power. You will put that rating inside. You will run your simulation, and you will see, are you overloading that line or not? This is something you will do. If you're overloading that line, that means you have to route power differently or change the line, right? So this is something we will do in this chapter as well. So we want to make sure that generators operate within a specified real and reactive power limit. So as we said, generators are an AC component. They have a certain apparent power that they are able to deliver. This apparent power is a combination of real and reactive power. Right? So reactive power is not an evil. It's something we have to live with, right? Because we need it, right? And we will see later that generators like to operate with some reactive power. They want to be able to operate with a lagging power factor if you want to maximize the amount of power that they're delivering. So this is how and we will look at the equivalent circuit of a generator in the phasor diagram later. They do not want to operate with leading power factor. So, and if you consume too much reactive power, you will limit the amount of apparent power that generator can deliver, right? So we have to make sure that we are not exceeding any of the limits. Transmission lines and transformers are not overloaded. We talked about that, so we will do that in this chapter. Okay, so as we said, this power flow problem is sometimes called a load flow problem, right? So you will see power engineers using either power flow or load flow. And it is always done. You're building a new plant, you will have to conduct load flow studies before you build your plant. Why? Because this is the type of study that helps you choose the ratings of the equipment. Right? You will always have a load flow study. There are other studies that power system people do, right? When you're building a new plant or expanding your system, you will start with a load flow study. But you will also be doing a harmonic study, you will also be doing some motor starting studies, you will also be doing whatever. Other types of studies. But this is typically the core. You will always start with this load flow type study. And as we, since it's nothing but an analogy for a 214, big circuits problem, what we do from a load flow study is determine all the node voltages, make sure that it's close to nominal values, look at all the currents and powers flowing in all the branches, and make sure that there are no overloads, match generation and load, that's one thing. And of course, you can also work on minimizing system losses. So you have different cables, right, in the power system. They have different impedances, right? So which path do you choose for power to flow will help you minimize the losses, right? So you may want to expand the city. The city is growing in a certain fashion. Your selection of transformer to feed the area of the city may be less efficient than your selection of another transformer to feed the same area of the city, right? So looking at some things like this, like losses in the system, is something that you can get from a power flow study. Scheduling generation to meet demand economically. So an extension power flow is something we will do in this chapter. There's an extension to power flow, I think it's chapter 12, right? Is when you add the economic constraints. Okay, so you will add the cost of fuel. So now in this chapter, we will only be dealing with the generators as sources, and we will not worry about the cost of fuel and stuff like that. So I don't know if this is a PV plant, or I don't care if it's a PV plant, or if it's a natural gas plant, or if it's a combined cycle plant. I don't care, right? But in chapter 12, there's another chapter called, a topic called economic dispatch. Economic dispatch is nothing but power flow, but considering the cost of the fuel or cost of power generation. We will not get into that, and it's really just an additional enhancement of what we're doing in the power flow work. We will add another equation to the system and solve that with the rest of the equations, right? So we don't have time to do it within this course, but basically in that case, you can now consider the various types of the power plants. You can consider all PV plants, wind plants. You can consider, because then they all have costs, right? And then if you consider their cost in the system, then you should be able to design a power system optimally from a cost perspective. Also making sure that your load and the generation are met, plus the losses, and etc. Everything else in the power flow problem. So economic dispatch is the power flow plus the cost perspective coming into. Okay, so that's why this is here. Idea of scheduling generation properly. So here we will schedule generation. So we will make sure that we have enough generation to meet the load, but without considering cost. Just considering the fact that we need to meet our loads. Economically is an economic dispatch. Determine the effect of injecting boost voltages on system loading and the adequacy of voltage regulation. This is talking about the transformer voltage taps and capacitors, capacitive static var compensators or capacitors addition in the system. Determine the stability margin between the two generators. So one of the things we will do is calculate the angles. Again, we have to calculate voltages and angles between every node, right? Generators work in sync. Like if you took 338, you did an experiment on generator synchronization, right? For those that took 338, you did one experiment on synchronizing a generator to the grid. And what you did there was look at, okay, you have a generator here and a grid here, three-phase grid, three-phase generator. I want to connect the two together. How do you do that? Before you connect, you look on this side and you look on this side. You make sure that the voltage as a magnitude and frequency on both sides is exactly the same. Of course, exactly, right? That's what you do. Of course, now it's done electronically. We don't need to do it. We can do it electronically now. But that's what you do. You look here and here, make sure that the voltage and angle and frequency, or voltage angle and magnitude, are exactly the same. They're exactly the same. You close the switch. If you close at that instant, are you actually pushing power into the system? You're not. At that instant, you're actually not pushing power into the system because the voltage magnitude and angle are exactly the same, right? They're exactly the same at that instant. So you're not actually pushing power into the system yet, right? Because the generator is not loaded. When as soon as the generator is loaded, what happens? As soon as the generator is loaded, it starts slowing down, right? As soon as the generator is loaded, it starts slowing down. And your job is to do what? Put in more mechanical power to speed it back up. Right, so that's what you have to keep doing. That's what generators. Electrical energy will cause torque on the generator's shaft. If you're transmitting electrical power, that means current is flowing in the generator. That means there's torque. If there's current in a time-varying magnetic field, then there's force, meaning there's torque. Right. So what's your job? This torque is actually going to slow down the generator. So your job is to put in more mechanical power. We will talk more about the generator later in this chapter, but your job is to put more mechanical power in, and in that case, go back to a reasonable angle difference between the bus you're delivering power to and the generator's terminal, right? As soon as you try to deliver power, there will be a slowdown in your generator. That slowdown means there's a phase shift in the angle between the rest of the power system and your generator. Right? So this small phase shift in angle is because you've started loading your generator. you cannot remove that completely. There will never be, I mean, there will never be, if they're exactly the same, if the voltage between the generator, the bus at your generator, and then the bus you're connected to is exactly the same, then you're not delivering power, right? So what you do is, there's a limit on the angle difference between your generator and the generator next door, right? So your generator is pushing power into the system. The generator next door is pushing power into the system. You've synchronized your generator to the grid, and now your loads are connected. They want to consume power. So what will that do? As soon as they start drawing current, because you're generating a voltage now, then there will be a torque on your shaft, and you will slow down a little bit. Meaning there will be your angle will be changing, right? Your angle will be changing. As soon as your angle changes, then you have to make sure that this angle change is not too large, because you have to make sure that all the generators in the system are operating with a reasonable angle difference, right? It's like people walking, imagine 4 people holding a stick and with 2 loads connected to the ends of the stick, and all 4 are pushing together. If all 4 are pushing together, again, some people are stronger than others, some people are faster than others, etc., etc. But at the end of the day, if the fastest person just keeps running, what's going to happen to the 4 people? They will just keep going around in loops, right? I mean, if one person is very fast, then they're not going to be pulling the load all together. They're going to be just doing something else, right? They're not doing the function that needs to be done. And that's exactly what happens with the generators, right? So the generators in a power system all have to have a reasonable angle difference between them, and that's called the stability limit. And we don't talk about stability margins here, but it's basic. We will talk a little bit about the maximum limit that the generator should be operating at. The maximum limit of that angle we will talk about. But the dynamics of that, we will not talk about, right? So we won't talk about the steady state performance of a system like this. But there is a dynamics related to that, of course, and this is affected by every other generator in the system and how your generator sees everybody else and they see you, etc., etc. So there's a differential equation tying this relationship together. So the motion of the generator, the inertia of the generator, there's a, of course, if the generator has a huge inertia, the change of that angle, the allowable change of that angle may not be the same as a generator with a small inertia, right? So a generator with smaller can recover that angle very quickly if you add a little bit more mechanical power, versus a large generator that's driven by a coal power plant where you have to, burn more coal to generate steam. The inertia of that system is a lot slower than the inertia of a system running from a gas turbine, or the inertia of a system like a PV power plant. PV, okay, there's sun, there's power, right? There's zero inertia almost, right? So it's that's another thing, right? How do you generate PV systems? How do you generate power and maintain your synchronization to the grid with many PV systems connected to the grid? You have to do the same thing that typical generators do, right? You still have to make sure that you maintain a certain voltage shift with respect to a reference angle that you have in your system, so that you remain synchronized. Otherwise, your 50 hertz will be completely out of sync with another 50 hertz in the system, and you will either go out of sync, or they will go out of sync, because you're all connected to the same circuit. The same circuit should have the same sort of voltage as a magnitude. And remember, we have to have 1 per unit around the circuit, right? So we typically have to have 1 per unit. Everybody has to have the same voltage, almost. And we typically want to have small voltage differences between each other, so that we're all supplying a reasonable amount of power. Reasonable means what? Remember, we're normalizing everybody. Everybody is normalized, right? So everybody is normalized with respect to their ability to generate power in this specific system, right? So if I'm generating 1 per unit power, that means I'm maxed out at my power. If I'm generating 1 per unit and the other guy is generating half per unit, it doesn't make sense that I generate more, right? If additional loads are connected to where I am, what am I going to do? In that case, I should sort of increase my angle so somebody else can pick up the slack. If I increase my angle, people know that I'm loaded. I have no additional ability to generate more power, so people maybe, okay, at some point, they may turn me off because I'm not economically producing power. I'm going to be overloaded. Another generator has the capacity to supply this load better. Right? So we will talk about about that in more detail. Yeah. Investigate the effect of temporary loss of generation and transmission. So we will do this as well. So you have a lab on this. So you will, look at the big power system and say, okay, if I lose this transmission line, this transformer, what's going to happen to my system? Typically, a utility does not allow you to go have a blackout in a city or a country if just because of losing one transformer, right? So there's what is called redundancy in the system, and we typically operate with an M-1 criteria. So M-1 meaning your system will continue to function even if you lose one major component. So Kahrama in that case means that any major electrical circuit will have to be supplied maybe through 2 transformers or through 2 separate generators, right? That's called M-1 redundancy. If you're in a factory like Qatar Steel or where it's or Ras Gas, for example, where you would, if you lose power, you would lose millions of dollars, right? So if in Qatar Steel, for example, if they lose power, what's going to happen to this melting pot of metal that they have? Maybe it will just solidify, right? And then they lose their process, and then they have to clean all this up. It's a big issue, right? So that case, they cannot operate with it. They will probably have an M-2 or M-3 type redundancy. I don't know, honestly, right? But this is sort of the criteria. Sort of the redundancy criteria is an important criteria. At the transmission level, it's probably M-1. More critical loads, they will go to M-2 probably. Your house, my house, they don't care. They don't care. There's a small distribution transformer right outside the compound, for example, or your house. Fine, if it fails, Sarah lost power. She cannot study for the exam. It's okay. She can send an email to Shihab and say, I didn't study. I will say nothing. I'm just kidding. But really, I mean, it's because it's a cost issue, right? It's a cost, right? It's you operate with a higher redundancy, then it's a bigger cost. So we will talk a little bit about that. Investigate the effect of rearranging circuits and incorporating new circuits. So this is something you can do with PowerFlow, obviously, since it's solving the circuit problem. Okay, so we typically run these load flow studies at minimum load conditions, maximum load conditions. Why do we do that? Because at maximum load conditions, there's a possibility of instability. So these angles of the generators can become very large. If the angle of the generators becomes very large, then there's a possibility that one of these generators loses its synchronization to the grid. It's no longer going to be synchronized with the grid, falls out. If one generator falls out of sync with the grid, you've lost all its power. If other generators are not able to pick up the slack, then you will have cascading losses, right? You lost this guy, so then you will lose this guy because this guy is overloaded, then you will lose this guy because, and then that's where you have a cascading blackout. And we've had some of those. In the US, for example, 2003, that was the big one, right? So we had in 2003 the whole Northeast. I don't know how many people lost power for quite a bit of time. Yeah, I think one of the recommendations what came out was cut the trees. Right? So you cut these trees, again, all these transmission lines maybe got shorted, they were overloaded, trees were pushing them together. That was one of the things that they were recommending, cut the trees because maybe they caused. I mean, with the winter storm. I think it was a winter storm, right? Was it a winter storm in 2003? Does anybody remember? No? It was some storm, I believe. There was some storm. These storms, lots of wind, ice, trees, etc., etc. You can have these cascading sort of overloads in different zones, different generators coming out of sync, and you have a cascading blackout. Yeah. So you typically conduct these simulations at maximum load and minimum load. Another reason why you would conduct at maximum and minimum is the voltage levels, right? Remember we said that we would add capacitors in the system? So these capacitors are great because they can help you control the voltage around the circuit, but at minimum voltage levels, they may push the system into leading power factor, right? If your motors are not on, the transformers are not loaded, and you have all these capacitors in the system, right? So you are now supplying reactive power into the system, right? You are increasing the leading power factor component in the system considerably without any lagging power factor component to balance it out. What will happen? You will operate in a leading power factor. Generators do not like to operate in the DC power factor. They actually limit their power. It actually limits their power. And we will see that from the phasor diagram of the generator. Okay. Just more jargon here. So we know, of course, loads are typically given as megavolt ampere at normal voltage. Yes. So as we said, that we are typically given loads as as powers, right? You have a 100 kilowatt or 100 MVA system to feed, right? We want to stick that into the system, and we want to calculate the voltages and currents. We are given powers, but we're not given voltages and currents typically. So, right? Because you want to construct a power system to feed these loads, right? So what are the node voltages and currents are unknown. What you know is the load powers, for example. Again, we said that this is a steady state solution and mainly for planning and operational purposes, but in a steady state case, we're not concerned about any transients in a load flow situation. We will, again, take everything and represent it as an equivalent circuit, right? Like we did for the transformers. Unlike the simple equivalent circuit I drew quickly for the transmission line that we're going to go back and later derive. And loads, of course, loads we know. I mean, we can represent loads as just in RLs or RCs or RC circuits. So we will take, our generators, our transformers. So now we have how many components? We have a limited number of components. We have generators, we have transformers, we have transmission lines, and we have loads. Really, that's all we have. So we will take, and we now know how to generator is a voltage source, transformer is a series impedance, transmission line is this short line model that I gave, and then loads is a load, single phase equivalent circuit of a load. If it's delta converted to star, and you have your equivalent circuit of a load. Take that and build your power flow problem. Do we need to do this if we have a simple circuit? No. Again, remember what we're doing is nothing but 214 type analysis, AC circuit analysis. Yeah. So if we have a simple circuit, just a generator, transformer, and a load, and one transmission line, it's not very interesting to do anything like this at all. Yeah. We can solve the circuit, and we'll have an example here. This is basically chapter 2 material here. What we're talking about is more large networks. These large networks are systems where we cannot take a million loops and solve the system, right? And we have many different information that's missing because we are given lots of power information and not voltage and current information. So we will see how to deal with that. And this is just justification for why we don't need to do this for a simple. This is a simple circuit, right? We have 1, 2, 3, 4, 5 nodes, for example, in a circuit like this. Again, this is something like what we did in chapter 2 and 3, right? So you have a motor here, I guess. Yeah, we can go through the example. Another example it's a review for chapter 3, for example. So it's you have a system here, generators feeding two loads. You have two loads fed by a single generator. You have domestic consumers, so that you're feeding with at a 0.8 power factor lagging, 20 MVA load at 6 kilovolts. And if the motor, and then the other one is an induction motor. If the motor starts at 5 times the full load current and 0 power factor lagging. So they're saying that the motor current, when you start this motor, you will have 5 times the rated current. So this is the rated current you can calculate from, of course, the rated voltage and rated power. So they're telling you that when it starts, it will have 5 times the full load current, and it will look exactly like an inductor. It will look completely like an inductor, like 0 power factor, meaning a pure inductor. Not even have any resistive components yet. This is the worst case calculation. The induction motor voltage is nominally 6 kilovolts. So nominally, when it's operating at rated condition, the voltage is 6 kilovolts. If I'm drawing 5 times the rated current, what is the effect of that on the system? If I draw a huge amount of rated current of current and from this load, what will that do to my nominal voltage? I will draw more current, meaning I will have a higher drop across this transformer, higher drop across the line, higher drop across this transformer, and hence, this bus bar here sees a voltage drop, right? Since there's a drop at every component, right? Then this bus bar will see a drop, a voltage drop, and this voltage drop will also affect these loads, right? So if you're starting a motor somewhere, and this starting phenomena of a motor causes such high currents to occur, it will cause voltage drops around the system, right? Which can affect your loads, right? If it affects your loads, maybe a load like yours can, for example, disconnect if the voltage goes below a certain value, right? So, and if you're not able to deal with that through the tapping of the transformer, then you have a problem, right? Your loads will disconnect, right? So this is in this problem they're asking you to solve. Okay, they're asking you what is the voltage dip on the domestic bus bar when the motor is started. So motor starting studies are something you would also do in a power system. So especially in an industrial power system, you would after you do conduct your load flow, you would also conduct your motor starting studies. You will look at the starting current of the motors and make sure that the voltage drops that are resultant of these motors starting will not cause your rest of your loads to disconnect. So that's another type of study that you typically conduct in a power system. Okay, so how do we do this? So this is a generator. So we draw a voltage source, transformer, impedance in series. This is a impedance in series. Another impedance in series just happens to be a capacitor, and then another transformer. But these two and these are in parallel, right? So this is a generator, transformer, impedance, and then two parallel branches with series impedances for the transformer, and then something representing the loads, right? That's the equivalent circuit. And initially the motor is not running, and then they start it. So we look at the case when the motor is not running, right? The motor is not running initially. I think that's what the solution does. So the motor is not running initially. What we would do is sort of eliminate this branch, right? Initially we'd eliminate this branch and solve the circuit, right? They're telling us that the load is 60 kilovolt, 20 MVA, 0.8 power factor lagging, so I can calculate the current here. And if the motor is not running, then this is the same current flowing in the rest of the system, right? So I can solve my circuit that way, and I can calculate the voltage at the load, I guess, from there. We'll look at the solution here. And then the motor will start. If the motor starts, they're telling us that this branch has 5 times more current. So we will see. So we will put this branch in the circuit now, and I guess we will put 5 times the rated current and see what the corresponding voltage drop would be. So they're asking us to do this in per unit on a base of 50 MVA and 132 kilovolt on the generator side. The generator side is here. So they're asking us to choose the base on the left here to be 132 kilovolts. So the base on the right here would be 33 between this, on the secondary of this transformer all the way until the primary of this transformer. And then on this side, the base would be 6.6. Makes sense because this is 6.6. This is a reasonable choice of base, right? Everybody's okay with this? So we'll look at the solution. So this is the circuit that we described. So first, we, of course, all the components are not on the, so here the power base is 50 MVA. This is 50 MVA, so nothing happens. This is 50 MVA, so nothing happens. 50 MVA, no problem. This is 25, and these are 25. So obviously, we're going to have to do a change of base for the transformers, for these transformers, right? The rest of these components, since we already chose our base voltages such that we match the equipment ratings, right? We match the generator rating, we match the transformer rating, we match the voltage of the transformers, but we didn't match the power. So we need to go back and calculate the bases, do a change of base for these two transformers. We also need to do a change of base for this one since it's calculated on a 50 MVA, because this is given in per unit. On a 50 MVA base, no change in base. This is not based on a 50 MVA base as well. So the power base is 50 MVA for this transmission line. So I don't have to go back and recalculate its impedance. So I will use this impedance as is, this impedance as is, this impedance as is. But I have to recalculate the impedances for these transformers. Right? So I do that for these transformers. And since the voltage is I chose the voltage bases around the transformers to be equal to the turns ratio, which happens to be the rating of the transformer. So I chose the base here to be 33 and the base here to be 6.6, which means that the voltages, the voltage over voltage squared, old over new, will still be 1, right? But the powers will have a ratio, and that's why you see the ratio of the power, right? So then we built this circuit. So this is the circuit that we have. So we have a 20 MVA load at 0.8 power factor lagging, and we have this induction motor here, and then the rest of them. So these impedances are the same. The voltage is 1 per unit, since we said that we will choose the base as 132 on the generator side. And then the transmission line impedance is the same. And we changed the transformer impedances. We represented the motor as a load here, and we put the load power over here. Okay. So before the induction motor starts, okay, since we're going to look at the motor starting, it means that the motor was not running before, right? So before the induction motor starts, IM is 0. The induction motor, this branch current is 0. And load voltage is equal to 1 per unit. So the load voltage here is equal to 1 per unit minus the drop across all of these, right? So that's what we have. So the voltage is equal to, on the load, is equal to 1 per unit minus the current times the impedance of everything. What's the impedance? It's the 0.04 plus 0.1, which is these two, and then minus 0.1, and then plus 0.2. So that's the full impedance. And then the current is what we will calculate from the ratings of the equipment, from the ratings of the rating of the load. So it's this is 10 to the 6, sorry. This is 20 times 10 to the 6, not 106. Okay, so this is it's a 20 MVA load, right? So, and it's rated at 6 kilovolts. So the induction motor, it's rated at 6 kilovolts. So they tell us that the rated load is 6 kilovolts. So I would like to calculate the rated current from there. So I calculate the current. So 20 divided by square root of 3 times 6. 6 is the line-to-line voltage. So S divided by square root of 3 times V is what we have here, and that's the rated current at a certain power factor. And since I'm solving everything in per unit, right, then I need to calculate what? My base quantities at the different locations. So I calculated my base, the base current at 6.6 kilovolt side. So this is that's the base in this zone was 6.6 kilovolts, right? So we will calculate the base current here. The base current is 50 is the base power divided by square root of 3 times the base line-to-line voltage, right? S divided by square root of 3 times V line-to-line. And that's the base power, which means I can calculate my per unit current on the load side to be a certain value, right? So then I can go back and substitute to my equation. So given my impedances are per unit, now I have my current in per unit. I can calculate my load voltage in per unit, which is 0.9404 per unit. If you want to go and figure out what your actual load voltage is, you multiply by the base, which is 4374 in the specific zone, you will get 6.204 kilovolts. Okay?
You multiply with 437, that's current.
Sorry. It's base voltage. Base voltage is what? 6.6. 6.6. Sorry. Okay. So that's what we had before the motor started, right? We had completely eliminated that branch that we have in there. Now I think what we'll do is you have your load current, and you will have now 5 times the motor current. So you go to power rating of the motor and calculate the induction motor current, right? So this is IM, induction motor current, and so it's 5 times the rated current. The rated current is the rated power, right? Rated current is what? S times 10 to the, so it's 15 MVA, right? The motor will be 15 MVA. Yeah, it's a 15 MVA motor, so 15,000 times 10 to the third. So again, excuse the typo. So it's 15,000 times 10 to the third. That's S divided by square root of 3 times the voltage, the rated voltage of the motor. Multiplied by that by 5, and that is 5 times the rated current of the motor, right? So then you will, of course, convert that to per unit, and the base does not change. The base in the 6.6 kV side, we already calculated it. It was 4374. So we now have the base, the per unit current for the induction motor, right? So we have the per unit current of the induction motor. We have the per unit current of the load, right? We have the per unit current of the induction motor, per unit current of the load. Add the two together, and that is the voltage drop. And then calculate the voltage drop across this load, and then the specific load here will only include the current of the load, right? So, and then subtract that from 1 per unit, right? So look, we'll have 1 per unit minus IM and IL together multiplied by this portion of the impedance, and then IL multiplied by this portion of the impedance to calculate the voltage across the load. Okay? So that's what they have here. The new load voltage is equal to 1 per unit minus IL plus IM together minus one of the impedances, minus Z1. Z1, I believe, is that all these impedances at the top here. These impedances here, right? And then minus IL, which is the load current in the branch, and then minus times ZL. Okay. So now you have a load. If you get, this is in per unit multiplied by the base, which is 6.6, and you get 5.82 kilovolts is your new bus voltage. So you went down from 6.2 kilovolts to 5.8 kilovolts. Is this acceptable or not? That depends on your system and your loads, right? So this is something we calculated using just whatever we knew from chapter 2 or chapter 3, right? This is basic chapter 2 and chapter 3 review. We want to do this on a big power system. So we cannot go through this similar process. And that's where the load flow comes into play, and how we formalize the system, formalize the solution into something more convenient to use a computer with. That's I guess the objective is to, okay, how do you generate something more convenient to use a computer with? So we'll start with a simple circuit, and we'll justify. We'll start this, and then we'll have to end the class. Okay. So let's see. I have a small power system here, composed of 3 buses, and there is an admittance connecting these 2 buses together, admittance connecting these 2 buses together, admittance connecting these 2 buses together. This is bus 1, bus 2, and then bus 3. This is Y12, this is Y13, this is Y23, and this is a voltage E1, this is a voltage E3, this is a voltage E2 with respect to some reference voltage. Right, this is E1 with respect to some reference, E2 with respect to some reference, E3 with respect to some reference. Yeah. Right. So how do we solve this using circuits? How do I calculate the currents? And I have, let's say I'm injecting a current here, I1, injecting a current here, I2, injecting a current here, I3. So I have these buses, these nodes in my circuit, and I have admittances connecting them, so impedances connecting the different portions of the circuit, and I have voltages E1 and E2 and E3, and I would like to, for example, calculate I1, I2, and I3, or I'm given I1 and I2 and I3, and I want to calculate E1 and E2 and E3, right? So how would you sort of go about doing this? From circuits, I know that I can write I1 as equal to what? So this is current coming into the branch. I can use KCL, right? So I can say current is coming into this node, and then current coming out of this node here, and then current coming out of this node here. So whatever's coming in is equal to whatever's going out, right? So I1 is equal to what? Come on. What? So this current, the branch here is equal to what? The voltage difference. So E1 minus E3. So V equals IR. Right? So I is equal to V over R, or multiplied by the admittance, right? I is equal to V times the admittance. Right? So E1 minus E2 times Y13 plus E1 minus E2 times Y12, right? And I can do this for I2, and I can do this for I3, correct? So if I do this for I2 and I3, I can rewrite this. So I can rewrite this as something like this as well. So I can rewrite this as, I have E1 common in both, right? So I can take this out as E1 here, and I can write this as Y13 plus Y12, correct? Minus E2 times Y12 minus E3 times Y13, right? So I wrote this as an I1 equal to some voltage E1 times some admittance, some voltage E2 times some admittance, some voltage E3 times some admittance. I can do this for I2 and I3. And if I do that, I can these are three equations, right? Three equations, and I have, if I'm given the currents, I should be able to find the voltages. If I give the voltages, I should be able to find the currents, right? So I can put them in matrix form, right? So I can construct a simple matrix, and I can sort of put them in a matrix, and then have a vector of currents, for example, on one side, a vector of voltages on the other side, and what we call admittance matrix in the middle, right? So that's something I skipped in chapter 2, sort of. They spent some time talking about network matrices, etc., etc. So this is where I'm covering it, right? So here's where we need it actually. So we will what's relating the currents and voltages is admittance matrix, or it's also called Y-bus. It's called the Y-bus matrix, or admittance matrix, whatever you want to call it. Yeah. So what we will find is very quickly I1, I2, and I3. Instead of let me write it down. E1, E2, E3 will look like this. Y12 plus Y13 minus Y12 minus Y13, and this is minus Y12 minus Y12 plus Y23 minus Y23 minus Y13 minus Y23 and Y13 plus Y23. And I need to draw this again because it has some value. y12, y13, y23. Right, so the admittance between buses 1 and 2, buses 2 and 3 is y23. Admittance between bus 1 and 3 is y13, and this is y12. So, and this is called my y bus matrix, or admittance matrix, or admittance matrix. So how does this admittance matrix look like? It has a certain structure, okay? Because you will be given a power system and you will be asked to solve. So you will automatically need to come up with this y bus somehow. Right? So how do you come up with y bus? By just looking at this circuit. So this is a system with 3 nodes, right? So the y bus will be a 3 by 3 matrix. Right? So this is a 3 by 3 matrix, okay? Right? And the diagonal elements of y bus will be the sum of the impedances connected to a specific bus. So this is 1, 2, 3, 1, 2, 3. Okay? So this element is called y11. It is the sum of the elements between at bus 1. So this is y11. y11 is the sum of the admittances connected to bus 1. So I go to bus 1 here. What is connected to it? This one and this one. So y12 plus y13. That's what we have here. y22 is the sum of the admittances connected to, this is not minus 1, this is y12 plus y23. Sorry, there's no negative sign here. So this is sum of admittances connected to bus 2. y12 plus y23, y12 plus y23. Sum of the admittances connected to bus 3, y13 plus y23. Right? y13 plus y23. So now I have all the diagonals elements are fine.
The diagonal element has a negative?
No, nothing. The diagonal elements don't have negative. y12 plus y13, y12 plus y23, y13 plus y23. Okay, so the diagonal elements don't have a negative sign. Okay, so all the diagonal elements are the sum of the admittances connected to a certain bus. Okay, and then the off diagonals, and of course the matrix is symmetric. If you look at this, same as this. If you look at this, same as this. This is same as this. Right? So the matrix is symmetric. Then we can calculate the bottom part and we write the top part. Right? So y21 is equal to y12. Right? So y21 is equal to y12. This is y21 and this is y12. They are both equal to minus y12. What is this? So the off diagonal elements are equal to the negative of the sum of the admittances connected between the two buses. So I have, this is y12, or y12 is y21. So I'm between bus 1 and bus 2. So I take the admittances between bus 1 and bus 2, add them together and add the negative sign. So the admittances between bus 1 and 2 happens to be y12 in this case. So it's just a single element, and I take it and multiply it by a negative sign and put it here and here. Of course, this becomes more relevant when I have something like my transmission line, right? That's why we look at the transmission line model. The transmission line model will have more than just the series admittance. Now I will have this shunt susceptance. That's where this will play a role. These things will play a role here in the off diagonals, right? So it's the, okay. No, sorry, they will play a role here. Sorry, they will play a role here. They will play a role here. They will play a role as if this is an admittance, because here you're adding up everything connected to that bus. So y11, if this is connected to bus 1, then you have to add this. If this is bus 1 and this is bus 2, right? And then for bus y22, you will have to add this one, because this is one of the admittances connected to bus 2, right? For y12, you just put the series element, because it's between buses 1 and 2. So negative of everything between buses 1 and 2. Same thing here. Negative between buses 1 and 3. Negative between buses 2 and 3. Right? So everybody's okay with this? Okay. So theoretically now, we should go. But theoretically now, if I construct this matrix, then if I'm given the voltages, I can calculate the currents. Right? If I'm given the currents, I should be able to inverse this matrix and calculate the voltages. only if this matrix is invertible. If you look at this matrix and sum up all of these now, you will find that y12, the sum of this row, this column, y12 plus y13 this goes away with this goes away with this, you're left with 0. So it's a linearly dependent matrix, right? So you cannot invert this matrix. So what do we do? What do we do? Where does this come from, by the way? This comes from the fact that the current flowing here, the current flowing in these branches, as long as the voltage differences E1 and E2 is a certain value, and E3, then the current will be the same. But I can have E1 and E2 be 10 volts and 5 volts, or I can have them be 15 volts and 10 volts. I can have them be 20 volts and 15 volts. The voltage difference is still 5, but the current is the same for the same admittance, right? But it's because of this infinite number of solutions that I can have to the system, for this system. So what we have to do is define one or fix one, right? That's how you would do this, right? I would fix one mathematically, okay? Mathematically, you would fix one, right? If this is a system where you cannot invert this Y bus, how do you do this? You would have to fix one of these voltages. Let's say you want to calculate all the voltages. You want to invert this. You cannot invert this. So what do? That means you have to define. Okay, fix one of them. Fix one of the quantities. If you fix one of these, it's like eliminating one of these rows or one of these columns. Let's say I fix E3. I make E3 a certain value, x, 1 per unit. If I make this as 1 per unit, for example, mathematically, okay, live with me for now, and then next class we'll understand why. We'll make this 1 per unit, then I can solve this problem, right? Because I cancel one row, one column, and then this matrix here is something I can invert. This becomes a 2 by 2 matrix, right? I know E3 now, right? If I know E3, then I can find E1 and E2. If I find E1 and E2, I can find I1 and I2, and I will be able to find I3 later, right? So if I fix one, I solve my problem. Another solution is something we will discuss next class. We have to stop here.